Start. Mahfuz Rahman, welcome.
Thank you. Hi, everyone. Today, I am going to talk about an evaluation toolkit. I mean, explainability evaluation toolkit. Quantas, a paper that has been published in 2023 in the Journal of Machine Learning. So the reason I have choose this paper is because the black box models have been very popular in recent years, but we are still struggling with its trustworthiness. That means we are still not sure that what kind of associations these models are learning. And that's why people from different domains are actually trying to understand the internal mechanisms and the associations they are learning from the data. So first of all, I will talk about what's the main reason that people are struggling with. For example, what we don't know and what we can do and what people are trying to do. For example, when we try to evaluate a black box model, we don't know what kind of associations they learn. So we are relying on different explainability approaches to generate explanations. So different methods are available and we are generating explanations, but as there is no consensus on the definition of explanations, so we are not in a position to say that the generated explanations are right or wrong. So there is no ground truth, there is no universally accepted correctness of explanations, and we still don't know that what properties our generated explanations should fulfill. So these are the main challenges. That's why we are not relying on people's intuitions, people's judgments. Rather, we are trying to objectify the evaluations of the explanations. But there are certain concerns that people are coming up with different evaluation metrics, but they also depend on different parameters. They also depend on how we are pre-processing our explanations, how we are normalizing our explanations, that sort of things. If we are taking absolute values or if we are taking sign values or what kind of normalization techniques we are using. Based on different parameters and pre-processing techniques and the normalization techniques, the studies have found that the ranking results, the explanation results, when we are evaluating them, they are producing very contrasting results. For some parameterizations, some methods are seemingly performing better, and some methods are in other pre-processing setting or in other normalization setting, some explanation methods are doing better. And sometimes the conclusions are one-sided because it depends on the original author of the metric. Because in many cases, they actually propose that metric to validate their own method. So that metric may not be universal for every domain. Okay. So here we are. So actually, we generated this figure for one of our grant proposals just to capture the current status of the post-hoc methods. So we have a bunch of methods available in the literature, but we are still not sure that how to evaluate those approaches so that we can trust one or some of them. And this evaluation can be done on multiple categories. For example, we can test for their faithfulness. We can test if they are focusing on what they should focus on, or if the generated explanation is very complex, or it is very simple, something like that. So we'll talk about all of these categories in details in the later slides, so I'm not spending much time here. At a glance, the The major categories of evaluations are actually faithfulness, robustness, localization, complexity, axiometric properties, and randomization. I will define all of these broader categories in next slides. But in this slide, I just want to mention that on these broader categories, how this toolkit actually compares with some other existing toolkits. For example, as we can see in the table that CAPTAM is very popular among researchers and they are using CAPTAM to generate explanations. But CAPTAM has not been actually designed to evaluate explanations. It is being used only to generate explanations. And it has only two metrics so far. That means one faithfulness metric and one robustness metric. So altogether, they have only two evaluation metrics to test. In contrast, as you can see that Quantas has 27 metrics available because this toolkit is actually not developed to generate explanations. It is developed to evaluate explanations. And one of the key features of Quantas is it can be used in conjunction with CAPTAM and Investigate. We can use both CAPTAM and Investigate under the same umbrella. And also we can see that they have already implemented 9 faithfulness metrics, 4 robustness metrics, 6 localization metrics, 3 complexity metrics, and they also tested 3 axioms and 2 randomization tests. Okay, so now I will try to define, actually I tried to make the slides more educative rather than present rather than similar ordinary presentation. So I will try to define all of the broader categories of evaluation so that we all can understand. For example, faithfulness. So what is faithfulness? So I am showing the upper arrow and the down arrow to mean that if the better score, higher score is better or the lower score is better. That means upper facing arrow means that better score, higher score is better. And the down facing arrow means lower score is better.
Low robustness, that's kind of counterintuitive.
Actually, not the lower robustness, it does not mean. It depends on the metric we'll be using. For example, if we measure, for example, in case of robustness, as you say, if we measure similarity to check robustness, if the similarity score is lower upon perturbation, that means the explanation method is more robust. Because we are perturbing the input and then generating explanations, then we are computing similarity, so lower is better.
All right, so the robustness metric is really measuring the similarity of inputs.
It's not just the input, it's the model too, right? If you perturb the model, it's also you can perturb the model, like the model weights and if the explainability varies a lot, it's also a robustness measure, right?
Actually, there are multiple metrics for robustness. So one is, for example, you perturb the input, then match the similarity, you compute the similarity with the original explanation. If it goes lower, what does it mean? That means the explanation is being changed a lot, right? Okay, we'll see because our explanation is stable when subject to slight perturbations in the input. So if we slightly perturb the input, what is our expectation? Our expectation is it will not change much.
Yeah, that sounds like an adversarial attacks, right?
Yeah, it will not change much.
Everything.
It is, and one point to note, it is not randomization test. Local robustness test is not randomization test. So we'll define it later. Okay, faithfulness. So faithfulness, faithfulness is defined in terms of two things. First of all, usually faithfulness is measured in terms of model, but faithfulness can also be measured in terms of data. But traditionally, people focus on faithfulness to the model. So what does faithfulness to the model actually mean? It means that the explanation should be faithful to the model. So how we can measure this faithfulness? Okay, the regions, the explanation is identifying as important. So if we take out of those regions from the explanations, does the model predictive accuracy or the confidence drop or not? Something like that. So if it does not change the predictive behavior or the confidence of the model, it means that explanation is not faithful.
That's kind of a question about.
Yeah. It's an important thing. Please ask question.
Imagine, like there is a dog or some animal in the picture.
Hmm?
It's easier to think about insects because I don't know much about them. And the prediction is this species of insect. Because it's, let's take black widow. Some of them have a cross on the back, like one of the poison spiders, right? And like it focuses on the cross. But there is another species that it also has the cross to mimicry it, but its toes are white or something like that. There is another outside of ROI thing that is not connected. And you add it, and I'm like, oh no, it's a different species.
Okay, yeah, that's the point of faithfulness to the data. So I said that there are two things. Faithfulness can be measured under in relation to two things: faithfulness to the data, faithfulness to the model. So when we say faithfulness to the model, an explanation is faithful to the model if we upload highly attributed results, it should drop the model's confidence. Whatever that regions, it may be artifact, completely artifact, it could be. Or it could be some meaningful regions.
Or it could be meaningful, yeah, you don't
Yeah,
know.
it could be meaningful, it could be artifact. But if the explanation to be faithful to the model, the model's confidence should drop if we occlude that region. That region could be artifact.
Okay, let's go on. I'm still kind of, I think the issue is tricky.
Yeah.
Like.
Yeah, but faithfulness to the data means the explanation should identify the domain relevant regions in the input. It should not identify artifact as Sergey was questioning. Okay, and let's define robustness. What is robustness? Robustness means if we slightly perturb the input for which the prediction will not change, the explanation ideally should not change. That is the robustness. And localization. So localization, this kind of metric is only applicable if we have ground truth data. For example, if we use synthetic data or if we have some kind of bounding box in our input, in our test data set, then we can use this metric and check if the generated explanations actually falls within the specified bounding box or not. Complexity actually it means that how many features this explanation is producing as important. If it identifies most of the regions of in the input space as important, it means it is very complex. It is not concise. And the randomization test is very similar to sanity checks we did in different cases. For example, perturbation to the model weights or basically perturbation to the model weights. And what we do here is we try to perturb the model weights gradually and see if the explanation quality deteriorates or if it remains the same as it was for the original model. And axiomatic metrics actually tries to test if the generated explanations follow some idealistic properties. For example, completeness. So completeness property is, for example, the sum of the attributions should be equal to the model's confidence, for example. This is one of the axioms. We will see few metrics under each broad category in the next slides. For example, let's talk about faithfulness metrics. So there are different faithfulness metrics available, but I just took two examples from the literature. One of them is faithfulness correlation. What it does is it iteratively selects some subset of features and then replaces them with some kind of non-informative baseline, maybe mean value or some kind of values, and then tries to see if the model's confidence drops or not. If the model confidence drops significantly for the highly attributed regions or highly attributed features, it means this explanation is faithful to the model. A similar thing goes for pixel flipping. It captures the impact of perturbing pixels in descending order. Okay, so what it does is it takes a pixel that has been attributed very highly and replaces it with some non-informative value, for example, mean or 0, and then sees if the performance, if the confidence of the model drops or not.
But we know that this is stochastic gradient descent trained models. The salt pepper noise is very common, right? There are lots of pixels sticking around very highly that don't have to do it with the region of interest if you look at them.
Yeah. Yes, these methods all have actually pitfalls. These methods are not foolproof. Okay, so another is local Lipschitz estimate. It tests the consistency in the explanation between adjacent examples. That means if we take, for example, for MNIST test dataset, if we take the digit 7, multiple samples of 7s, all are similar samples, are the explanations, are the generated explanations very similar for all 7, something like that. Max sensitivity. So this is robustness metrics actually. We are now talking about robustness metrics. Max sensitivity measures the maximum sensitivity of an explanation using Monte Carlo sampling in a neighborhood of some radius. Right? So ideally, what should we expect? We should expect the same thing as we are talking about the MNIST digits. For example, if we take multiple samples of digit 6 and or if we take a sample of, for example, only one sample and perturb within a small region, we would expect, if the model prediction does not change, we would expect the explanation would not change much.
Oh, okay. So like your ROI, whatever doesn't get diffused, it's still the same. Like
it looks same, the prediction will remain same. So we would expect the explanation would also remain same. Something like that. Pointing game, localization, these two metrics are actually from localization evaluation criteria. So the first one is pointing game. It checks whether attribution with the highest score is located within the targeted object. I found it very interesting because sometimes we have seen that the attribution values may become very random. Maybe some unwanted regions has very high attribution values. The pointing game checks if the highest pixel, for example, the highest highly attributed pixel remains in the meaningful region or unintended region, something like that.
Is this an automated method? So they just look within the bounding box of the object or within a segmentation of the object?
Yes, you can only use localization matrix if you have bounding box or some kind of ground truth.
Right.
If you have, yes. And relevance rank accuracy, this is similar to what we used earlier, maybe sir we can recall. We had some ground truth data set with top down bar, we have some specific ground truth, so we use this metric, relevance rank accuracy, so it measures the ratio of highly attributed pixels within a ground truth mask towards the size of the ground truth mask. That means how many highly attributed pixels falls within the ground truth mask. Okay,
Yeah,
complex.
we have invented some of those metrics.
Yeah,
ourselves.
but someone
like-
has published this.
Yeah,
And they have
yeah.
named it, for example, relevance rank accuracy. This is the same thing we tried for our synthetic data set.
Yeah, we've tried multiple of those metrics, just came up with them on the spot. Don't think of those metrics as rocket science or anything.
Yeah,
It's
yeah,
just
yeah.
like the first thing that comes to mind, and then,
This is exactly the same thing.
yeah, like robustness, you've done a lot and things like that.
Makes sense you get those that are. Like kind of depending on a bounding box existing or something coming from CV, I think it makes a lot of sense. We don't have that kind of stuff usually with the brain data though.
Yeah,
We've got ROIs, but. It's a little bit tougher.
but for
Pick which ones.
for segmentation trusts, maybe we have, right?
Yeah, for segmentation, we do. But again, like it's a question. Right, for segmentation, do you want it to be looking at the actual matter that it's segmenting or matter around it, right? So if you were looking at, you're doing gray white matter segmentation, you did that metric only within gray matter regions, might give you a low score, but it's still fine. Because it might actually need to know stuff about regions outside of the gray matter
Right,
to
right.
do stuff. So I can see potential problematic with these kind of metrics.
Yeah, maybe let's go to the end of the slides because I have some philosophical inclination here. It's like this, what interpretation means, like what are we trying to capture? Like, is it about gnoseology, like how we know what we know, or like what? But let's move on. Like, I don't want to start here yet.
Okay, so that is the philosophical discussion on explanation.
Yeah, like what does it mean to be able to explain? Like they're trying to quantify everything, but what they end up is a soup of stuff that, how do I know which one is relevant, or like what is the guiding principle for me to select a metric, even if I cannot define what understanding is?
I think it's not an answerable question.
Okay, so
I hope it is answerable at least
For a
context.
specific, I mean, generally speaking, no, maybe not, like in the sort of grand philosophical sense, but, you know, I would argue that for most problems, it is an answerable question. If you have a specific problem that you're trying to solve, then there should be a metric that will give you the answer you're looking for.
Arguable.
And one thing
I don't want to distract us too much,
okay,
but I think about like, giving a human explanation. Why is that a duck? I could describe to you why I think it's a duck. But ultimately what you count is a valid explanation is very up for grabs based on, what you think
So,
counts.
Okay, but
let-
Valid reason.
let's keep some time for this discussion.
I think it's to the field.
Yeah,
to the
it's
field.
interesting. Okay, so isparseness, so I will not define as we wrote, as I wrote on the slide, but I will talk just based on how I understood. So isparseness means ideally the explanation should be very concise. It should not identify all of the regions or most of the regions within the input. It should be very smaller regions, so that, okay, we are seeing only the nose or eyes of the dog to identify that this is dog, something like that. It should not identify body, nose, face, ears, legs. It should not be like that. It should be concise. Effective complexity, it measures how many attributions in absolute values are exceeding a certain threshold. Same here, that means how many highly attributed pixels or highly attributed features are there in the explanation. It should again be smaller. It should not be most of the area within the. Okay, randomization. So this is very familiar to us, model parameter randomizations. Ideally, what we do is we try to gradually randomize the model weights and tries to see that if the explanation changes, that means ideally, if the model, the explanation, if the explanation is sensitive to the model parameters, and if we randomize the models, then the explanation should change. Another one is random logic test. Sometimes we have seen when we do our synthetic experiments, maybe Saidi can recall, that sometimes we try to generate explanations based on class 0, and we also try to generate explanation with respect to class 1. And sometimes, unfortunately, we found in some cases the explanations are same.
Well, they kind of mirror each other, right, as well,
Yeah,
or like exactly the same.
yeah, we tried for binary class. But for example, you are dealing with multi-class, 10 class or 100 class. So the explanation for dog class should not be the same as the explanation for the cat class. It should differ, ideally. So this.
Well,
But there would be overlap there because they're quadrupeds.
Yeah, but if it looks at the nose and the eyes, you can easily distinguish dog and cat by looking at the same features, the nose and eyes.
Okay, let's add another class. Let's cat, dog, bird. It should differ. So,
But still, the statement calls, if you see a beak, it's probably not a cat and a dog. It's like eyes, nose, it's still working, right?
Mhm.
It's difficult to come up with example, I understand.
Yeah.
Well, I mean,
So you're watching the same feature and your feature has depth to it, that it can distinguish multiple things. A single feature
I
may
mean,
be able to distinguish multiple classes.
might be betraying my
Mhm.
like the time it's been since I did image recognition, but you first have to identify whether it is a beak or a nose, and that's
Well, but the model is showing you, here's the hotspot I'm looking at, or this hotspot will affect my classification. And what is questionable about this entire field, for the record, since we're recording, is that it's totally observer dependent. Because we are looking at the hotspots in the images that we can interpret. And hotspots overlap, we can interpret. We're gullible, we're like, yeah, I believe it, blah, blah, blah. Look at something like, I don't know, star sky survey, something that you're not specialist in, something like that. And then what? Then like neither the image nor the hotspots have no meaning to me. Can I learn anything from it then? So like there is a third component here, always a human who knows what's going on. And it's kind of, yeah. So I'm talking about knowledge discovery. We're not discovering any knowledge, we're kind of assisting the humans to confirmation bias, kind of confirm, oh yeah, this is what I expected to see. Okay, you're good, it's good model.
Yeah, ultimately you have to, just philosophical discussion, ultimately you have to rely on humans. Because the humans will be using this is my point of view, the humans will be using this system in different applications, right? So ultimately it has to be understandable to humans.
I think it's I'm just kind of like brainstorming here, like, it seems like the changes in scores you should see between classes should be proportional to like the difference in the sizes of their segmentation maps. But you have to sort of make an assumption about how big the object would be. And have some sort of notion of what, like, in this image, it's gonna be, take up this much, because it could be like closer to the camera or further away. So it'd take up more or less the field of view, so you have to have like an idea of like, if these two objects were at the same distance from the camera.
Yeah, it will
Like-
require expert intuition.
Yeah, but I mean, I think that that requires intuition because it hasn't been formalized, like the more you formalize, like the equations that would involve.
In,
I
well,
think, I think,
the other problem is like how. What do you, are we talking about a cluttered image where there are other objects that you can compare the object of interest to, or is it, is it something against a blank wall where you have no way to compare, you have no way to judge the size of the object, because there's nothing to compare it to.
That's true, but you can kind of get things, so it's
Okay.
like, if you assume like the same type of object was in the same position, but anyway, maybe not.
Okay, so another broader category is called axiometric matrix. So I just put two things I found interesting. One of them is non-sensitivity. It ensures that a method assigns zero importance only to features to which the model is not functionally dependent on. That means if there is some pixel or some features on which the model is not dependent on, the feature importance score for that pixel should be zero. If it is not functional.
It's relevant to how you started at first faithfulness, right? It's relevant to faithfulness, or it's the same as faithfulness, it feels to me. That if you change something that is irrelevant.
Yeah.
It's like,
Axiometric has connection with faithfulness, yes.
Okay.
Yeah. And another one is input invariance. I also found this one very interesting. For example, if you just shift your input, for example, if you add +10 with each of the pixels, something like that.
or like scale that William was talking about. How does it matter if my cat large or small? It's.
Yeah.
I think that's just like a linear shift though.
Yeah, the linear shift, right? Mean
I don't
shift,
think
for
the
example.
scaling would not be,
Well, scaling is like a shift in the field of view,
yeah.
just to
definitely.
defend myself,
Yeah,
but
yeah.
I get what you mean.
So
It's just like.
these authors,
depends.
these Kindermans, they have showed, they actually proposed these axioms, input invariance. They said, if we change the input in some way, that ideally would not change the model's behavior and model's predictions, only it will change the biases. They have created a model and then for the original input, then they change the input with some mean shift and then change the bias of the first layer.
According, you have to do it manually.
Manually, they did it manually.
Yeah, yeah.
They did
The model
manually
will-
and then theoretically they showed
Mhm.
that the score at each layer, activations at each layer of the model and the final prediction, confidence, everything will remain same. So they said, if the activations and the final confidence remain same, then the gradient will not change. The gradient of the output with respect to input will not change. And that is called input invariance. But they discovered that some methods actually cannot maintain this input invariance. That is, model behavior is not changing, but in their case, explanation is changing. Okay.
The gradient doesn't change and, yeah.
Yeah, but the explanation is changing for some methods. Okay, so this is the explanation I have already given. For example, gradient and signal methods satisfy these input invariance. This is not relevant to Quantas, but I found this interesting. That's why I put this slide here. So gradient and signal method. Signal method means guided backpropagation, decombinate, deep Taylor decomposition, that kind of methods. They are decombinate and guided backpropagation. Sorry. So these methods actually satisfy input invariance. That means the explanations do not change in their case. But gradient times input, it changes. And it should change, right? Gradient is not changing. We have changed input, so it would change. IZ and other attribution value, attribution explanation, for example, deep Taylor decomposition, they don't satisfy input invariance. Okay, so I will not go into the details of this. So this is how we can generate we can evaluate we can evaluate explanations using Quantas. First of all, we have to identify which metric we'll be using, and we have to initialize those metric first. And then we have to load our model, provide our inputs and the attribution values and all of these parameters. And then calculate scores, and this is the result. For example, here we are showing only the sensitivity analysis on faithfulness correlation. So it is showing that based on different ranking strategy. For example, as we can see that we are working on single metric faithfulness correlation, but it has some other arguments, other parameters, like which kind of baseline strategies we'll be using, what will be the size of the subsets, something like that. So based on different ranking strategies, different methods have been ranked actually differently. For example, as you can see in this figure, that saliency in 41% cases, it has been ranked as the first one. That means it has been ranked as the highest or most reliable one, most faithful one. And in 8% cases, gradient shape has been recognized as most faithful one. In 25% cases, IG has been ranked as the most faithful one. Similar to IG, fusion gradient has been ranked 25% of cases as the most faithful one.
This is just one model, one problem, or that's.
One model, one evaluation metric, but the parameters are different.
Yeah, CCO and CSO high ranked.
Yeah.
Throw some flags.
But only for one metric, faithfulness correlation.
Oh, it's just for faithfulness.
Yeah. And using Quantas is very easy. And I just put this one just to show an example. So for example, you will be evaluating pixel flipping, this evaluation metric. So what you will do, you will just define the metric first. That means pixel flipping equal Quantas dot, you are just initializing the metric, and then you provide your model, you provide your input and the attribution. A batch means the attribution batch, that means saliency batch, and then you get your scores and then plot. This figure is actually directly taken from their paper. I was actually struggling understanding these results. So they are trying to show the evaluation results on the pixel flipping metric for the four methods: saliency, integrated gradients, gradient shape, and fusion grad. As we can see that they are evaluating based on different ranking strategies. Pixel flipping means you are taking highly attributed pixel and replacing it with some non-informative values. You can replace it with mean, some random value, some black value, or some white values, for example. And then rank all of the methods according to these rank strategies. So as you can see, if you use mean replacement strategies, the ranking will differ if you use random replacement strategies. So that's the reason of showing here that if that this evaluation metric even cannot tell with certainty that these explanation methods are good or these explanation methods are bad. It will entirely depend on how you are ranking, what kind of parameters you are using. And so we have to decide our parameters based on our domain knowledge or the problem we are handling. Any other question here?
So the last one, the fusion grad and the pentagram. So the more area of the pentagram, the better the method, or it's reverse, it's more sensitive to those kind of perturbation.
Okay, so this is called spider graph. As we can see, the origin is at the center. And it is actually creating multiple axes. That means there is an axis for faithfulness, for robustness, for complexity, for randomization, and for localization. So the further the point is from the origin for that axis, better its sensitivity to that evaluation criteria.
So the larger the area, the better.
Yeah,
But then the result on this ladybug looks like something like your guided grants or something like that.
fusion graph.
Like, yeah. But what are they doing? Are they somehow?
But maybe not, because for faithfulness, as I discussed in the earlier slide, that for faithfulness, higher score is good, right?
Well, I assume anything is higher score is good. I don't understand. Yeah.
No. Faithfulness, higher score is good, that means higher drop is good. If the performance of if the confidence of the model drops much, it is more faithful. They have defined these metrics in that way, actually.
I think for that graph, that would be hugely confusing if they made
Yeah.
one increase and one decrease. They'd
Yeah,
flip that.
Localization higher means better, that means more overlap. Better. Robustness lower better means explanation is not changing much if we slightly perturb the input. It means that. So for randomization, higher is better. Complexity lower is better. Because randomization actually tests, if you perturb the model, then the explanation should change. The more dramatic the change will be, the more reliable the method is. So I would say this spider graph actually reflects that notion. For example, the complexity for the red one is, it shows higher, right? The complexity is fusion grad, it is higher. But as we can see from the saliency map, it is very concise, right? Compared to saliency. If we just compare saliency with fusion grad, first one with last one.
Localized, you mean sparse?
Yeah, it is very concise. That means highly attributed regions are small compared to saliency map. So its complexity is low according to the definition.
Yeah, that's weird now that you mentioned. So I'm just looking at like comparing the methods. So is if green is saliency then?
Yes.
Spider graph,
yes,
okay.
Yeah.
So it's saying, so it's less on the complexity axis, saying that it's more complex.
Which one? The green one?
The green on the spider graph, yeah, so it's lower on the complexity axis, right?
Yeah, lower on the complexity axis, right?
Yeah.
Yeah, so it is, I think it is in contrary to the definition.
Yeah, okay.
So this is not helpful figure then.
Yeah,
Because it's not consistent, like all the axes, the larger should be better. And
Yes,
then,
yes.
like William, back to your paper, the consistent, otherwise the readers just don't.
No, I think it is consistent, they're flipping some of the metrics. So
Yeah,
that
but
bigger
then
is
it's
better.
coming
Yeah.
inconsistent with the expectation, and either all out are good or all in are good.
Well, it is all out are good, it's just that with complexity, so it's the red is further out, so it's the least complex, they just flipped the metric to make that work.
Yes.
That's what I was saying.
I think.
Well, but then call it simplicity.
Yeah, exactly, I mean, that would, yes, I agree with that.
So I think what they did not do is they did not explain this figure. They actually did not explain this figure well. I struggled a lot and then went to their GitHub, then tried to understand what's going on.
Yeah.
This is even just for one test, though. This is just after the pixel flipping, or?
Yeah, it's just for pixel flipping.
Yeah.
But I would say, as Brad was saying, that they actually flipped their definition. The first definition was saying that lower the complexity, better. But for this spider graph, it seems in all cases higher the better.
Okay.
Yeah, that would only make sense.
Yeah.
So with Fusion Grad, what does it do? It's like adds the stuff or cancels the stuff from each layer. And like, why is it so?
I'm actually
Same
still,
model.
I'm not familiar with this method, but maybe I'm not sure if you looked at this comment, particular comment. One reviewer said, please include this paper. You know,
Yeah, in the IGG,
Fusion Grad.
or GGIG, right?
No.
In the GGIG, or in the review paper.
In the review paper, they said,
Yeah, because it's very related to GGIG in the performance, like yours also kind of highlights it.
Yeah.
It's a little different, tracing the bar, but it's kind of sparse.
Mhm.
Okay,
okay, so something they have said that they have some benefits, but they have also some cautions. That Quantas is very highly customizable. You can use it with Captam, you can use it with Investigate, you can use it if you already have your own explanation method, you can also use that your own method with this Quantas toolkit. And also you can customize the existing metrics. And API documentation is available, and you can also define your own supporting functions. And one thing they have actually mentioned that we should be very careful because the evaluation outcomes are highly sensitive to the parameters, as we are talking about while discussing about the rankings. And as it varies a lot, they actually try to put lots of warnings in their codes. If you evaluate, they will give you warnings several times. You should not trust this evaluation. You should be mindful about these, and be mindful about your domain, something like that.
That's great.
And they also say that you should not also rely on any of the metric because one size actually, there is no one size fits all evaluation metric. And whenever we'll be using some metric, we must calibrate those metric to satisfy our contextualized needs.
that's what we were talking about. in the
Yes,
beginning.
and this is the final one, and now we'll take questions and we'll start discussing about the philosophy.
I don't think we have time for philosophy and question.
Oh, don't have.
We have to go to the next.
Okay, so.
Yeah, there's the map next door.
Okay, so ultimately, explanations must make sense to humans. This is from another paper. They have tried to evaluate based on humans evaluations in multiple test cases, in multiple task scenarios. And tried to rank all of these explanation methods. And
This is highly, highly non-scientific though. It's like kids do a lot of stuff, they achieve their goals, they understand nothing, they're reinforcement learning agents. They want the candy, they will do any psychology trick, they don't know how it works, they don't care about any science behind that. As soon as they figure out the trick, they will get the candy from you. Do they understand? No, the same thing here,
I mean,
human
you're
understand.
hitting at a core
Yeah.
problem, even in pedagogy, is how do you write a good exam, right? To know that a student knows the material.
Yeah,
It's the same question, like
The same.
it's unanswerable, I think. I think it's impossible to write a perfect exam or ask a perfect question to get into someone's brain to know exactly what they're, if they understand it or not, you kind of.
but
Your
I'm
best
not that
first.
pessimistic, but I see where you're coming from.
No, you have best heuristics, you can't get exact, it's impossible.
But as we were discussing the other day, there are two kinds of needs. One need is to satisfy the predictive capacity of the model. So you test on diverse data sets and see if it still can do well. If it does, and if your need is to only get good predictive capacity, then go with that model. But if your goal is to look for domain knowledge, look for some knowledge discovery, something new, or
Yeah, that is my goal.
something new, or you will be applying this model in some dangerous situation, risky situations. You will be using this model to treat patients, something, or you will be dealing with people for their financial services. law enforcement agencies to give verdict, something like that. So you have to be very careful and you have to trust your intuitions.
I'm writing a LinkedIn post about that.
Thanks, Matt.
Yeah, thank you, very good.
Maybe
Yeah.
this is
That's okay.
positive, down to false positive, and false negative, like the receiver operating characters like that.
It's not that simple.
Not that simple.
Yeah, thanks everyone for coming. Important topic for us.